Hello and welcome back. Today we get to play with section 10.4 on the hyperbola. So we'll do sort of the exact definition first, and then we'll kind of see what it means. So a hyperbola, another collection of points we're still working in a plane, of course, such that the difference of the distances between the point and two fixed points, those are still the foci, is constant. So the ellipse was the sum of the two distances being a constant. Now we have the difference of the two distances being a constant. So let's kind of develop this without loss of generality. Let the hyperbola be centered on the origin. And we'll have it open left and right. So the shape of a hyperbola, we get either opening left and right or opening up and down. We're going to have this one opening left and right. Our foci are going to be at C0, negative C0. Vertices at A0, minus A0. So again, this one, we're going to make the assumption it's opening left-right, centered on the origin, and we have the vertices A0, minus A0, and our foci are just a little bit past that, C0 and minus C0. So let's start with just the A0 and we'll look at the two distances. So here's one of the distances. Here is the other. I'm just trying to sort of highlight them. So distance 1 minus distance 2 here. Distance number 1 is a minus negative c, which turns into a plus c. Distance 2 would be c minus a. So distance 1 minus distance 2 turns into a 2a. The c minus c drops out, and minus a negative a is really a plus a. Now if we did this with the other point, we would have come up with a negative 2a. So if we did the left side of this two-piece curve, we would have a distance of negative 2a. So now let's look at some other arbitrary point, xy. And same deal, we're going to look at those distances. So distance 1, square root of x squared plus, or x plus c quantity squared. So x minus a minus c turns into x plus c. Y minus 0 is just y. So plus y squared, distance 2, square root of change in x squared plus change in y squared, x minus c squared plus y squared. So we know the difference of these guys is either 2a or a negative 2a. So I'm going to go ahead and slide this one over the other side. So square root of x minus c, that one was a plus c, my apologies, x plus c squared plus y squared, distance 1 was a plus c, equals plus or minus 2a plus square root of x minus c quantity squared plus y squared. We got one of the radicals by itself. Think back to your Math 100 days and college algebra days. Finally, we are undoing the square root by squaring both sides. So x plus c quantity squared plus y squared is worth squaring this right-hand side. We have 4a squared. Then we have plus 2a times our square root plus another 2a times our square root. So plus 4a times our square root. And then plus our square root times itself. We'll get the argument out from under the radical. Right away I noticed the y squared and the y squared are going to drop for us. We'll get some other cancellation happening once we do a little expanding on our x plus and minus c's. So left side x plus c quantity squared, x squared plus 2cx plus c squared. Right side we still have that 4a squared from the front of the line. We still have our plus 4a times our radical, x minus c quantity squared plus y squared. And expanding our x minus c quantity squared, we have x squared minus 2cx plus c squared. And our y's were already dropped out. Okay, as promised, more cancellation. Goodbye to our x squares on both sides of the equation. Goodbye to our plus c squares on both sides. And now I can start moving some of this other stuff to the left side to get this radical closer to being by itself. So I have 2cx plus another 2cx is 4cx. Minus 4a squared is worth 4a times our square root. Notice we can divide both sides through by 4 and get cx minus a squared is a times our square root. Okay, so we can now square both sides again. So squaring the left side, we get c squared x squared minus 2a squared cx plus a to the fourth. Squaring the right-hand side, a by a is a squared, and then we get rid of our square root. So x minus c squared plus y squared are all in that. A little bit of expanding to do on the right side. The left side is just along for the ride at the moment. So a squared by c squared minus 2cx plus c squared plus y squared. And go ahead and knock down those parentheses. Okay, a little bit more cancellation happening now. We have minus 2a squared cx minus 2a squared cx. And let's see, do we have any other canceling? Not at the moment. So now we can get everything with a variable onto one side. Remember, a and c are just arbitrary constants. X and y are input and output variables, respectively. So I'll leave the c squared x squared over here. This a to the fourth is moving to the other side. All right, so I've dealt with him, a squared x squared moving to the other side. A squared c squared staying put. A squared y squared, that's got our output variable below left-hand side of the equation. So we can pull an x squared from the first two terms, and we have c squared minus a squared quantity times x squared minus a squared y squared is worth, we can factor an a squared from these two guys, and just to sort of have the notation look a little more consistent, I'll put this guy in the back, this guy in the front. So now we're going to use a quick little let line. Let b squared equal c squared minus a squared. So we have b squared x squared minus a squared y squared is a squared b squared. So all of my c squared minus a squareds turn into b squares. We'll divide everything by a squared b squared. So then we have x squared over a squared minus y squared over b squared is worth 1. So it looks a lot like the ellipse formula. Instead of a plus in the middle, we have a minus in the middle. If we want to move that around, so if we want our center to change from the origin to, say, hk, then just x minus h quantity squared over a squared plus y minus k quantity squared over b squared is still worth 1. Our let line is also, remember, C did represent the location of the foci, so how far left and right we go, or up and down we go, depending on if it's x squared first or y squared first. The relationship would be c squared is a squared plus b squared. So that's helpful in finding our location for the foci. So if we wanted this to open up and down instead, we could turn this, draw opening up and down. That would turn into y minus k quantity squared over a squared, minus x minus h quantity squared over b squared is still worth 1. Now, as far as drawing the hyperbola, we also have asymptotes. Find the vertices that are actually on this, then find what would have been vertices if we had an ellipse. So in other words, if this had been a plus sign in the middle, find the other two minor axis vertices, draw a rectangle with vertices as midpoints of each side. diagonals are the asymptotes. Alright, so let's put some of this to work. So we'll start with one that's pretty much already set up for us. X minus 2 squared over 4 squared minus y plus 3 quantity squared over 5 squared is worth a 1. So they already did the work. They got it into this nice, neat, pretty format. So our center, just work on your shifting. So x shifted to the right 2, y shifted down 3. There's our new center. Since we have the format of x squared minus y squared, this one opens left and right as opposed to up and down. So our vertices are going to go along this way. So our if we're picturing y being a negative 3, that would drop that entire term out. X minus 2 quantity squared is 4 squared, so x minus 2 is plus or minus 4. So we're moving left and right 4. So left 4, we're at negative 2, negative 3. Right 4, we're at positive 6, negative 3. And the foci, again, since this is left and right, the foci are going to move left and right from the center as opposed to up and down from the center. So c squared is a squared plus b squared. So c squared, 16 and 25, 41. So c is plus or minus root 41. So then that's how far we'll move left and right from our center. So we have 2 minus root 41, stay at negative 3, and 2 plus root 41. Y stays again at negative 3. So our hypothetical vertices, they don't actually exist because if x is worth 2, we have a perfect square equaling a negative. If we multiply both sides by negative 5 squared, we would have y plus 3 quantity squared is negative 5 squared. Y plus 3 is plus or minus 5i. That kicks us off of the real numbers. And remember, applying it when we're sketching these xy graphs are just two real number lines. So hypothetically, we would have done our other sort of, we'll think of them as the ellipse vertices that are not on the hyperbola, not an officially sanctioned term. What if vertices, ellipse vertices, we would have moved up and down 5 from the center. So we could also use as reference points 2 moving up 5 would put us at 2, and 2 moving down 5 would put us at negative 8. So that's also going to help us get the equation for equations plural for asymptotes. Okay, so our center 2, negative 3. Pull that there. Help get our bearings, our vertices, negative 2, negative 3. And 6, negative 3. So 1, 2, 3, 4 units that way. And hypothetical what if ellipse vertices. We have one at 2, 2, and we have one at 2, negative 8. And we do have our foci. Root 41 is about 6.40. So 2 plus 6.40, 8.40. And we're staying at negative 3. So here's 8. Here's a little under 8.5. And then about the same distance out on the other side. So 1, 2, and change more. So there's our foci. So now we can draw our box, which is going to help us figure out our asymptotes. So the first corner of our box, our x value there is at a 6, and our y value is at a 2, and the other corner down here, our y value, we're down here at negative 8, our x value is at a negative 2. So connecting those up with the dotted line, we have one of our two asymptotes. Connecting these guys up, the other diagonal of the rectangle, and here's our sketch. And we'll just do, for time's sake, together, we're just going to do the equation of this first asymptote, and I'll assume that you can also then, you'll be able to figure out how to get the second asymptote. All right, so slope number 1 for asymptote 1, we have 2 minus negative 8 over 6 minus negative 2. So that's 10/8, which is 5/4. So then change in y is slope times change in x. So y is 5/4 of x minus, that would be, factor out the 2's there, 3, 5/3, 15/2. And then 2 is the same as 4/2. So y is 5/4 of x minus 11/2 is asymptote number 1. So again, I'm going to ask you to find asymptote number 2. So there's our pretty good sketch of the hyperbola with lots and lots of information on it. Okay, so I would like to do one where we are going up and down. So let's try one where we have to do a little bit of extra work here. So let's say we have negative 3x squared plus y squared minus 6x plus 8y plus 4 is 0. All right, so we're going to rearrange this. Notice that the y squared was positive, the x squared was negative. I'm going to put the y squares out front, which means it's going to drag that 8y with it. I'll leave a little room here, minus 3x squared and the minus 6x, and we'll scooch that forward to the other side. A little bit of factoring, then we'll complete the square. So y squared plus 8y negative 3 by x squared minus 2x equals negative 4. And let's see, completing the square, plus 16 and plus 16. And a plus 1, which is really worth a minus 3. So y plus 4 quantity squared minus 3 times x minus 1 quantity squared is worth, let's see, 16 minus 7 is 9. So we'll divide everybody by 9. So y plus 4 quantity squared over 3 squared minus x minus 1 quantity squared over 3, which is root 3 squared, equals 1. So our center, 1, negative 4. Our vertices, because the y goes first, this one opens up and down. So our vertices, we're going to move up and down by 3. So that x is going to stay parked, and we're going to move up and down 3. So up 3 and down 3. Foci c squared is a squared plus b squared. So c squared is 3 squared plus root 3 squared. So c squared is 9 plus 3. C squared is 12. So c is plus or minus 2 root 3. And again, we're going to go up and down from the center. So negative 4 plus 2 root 3. Negative 4 minus 2 root 3. The x-axis, or x value, still stayed at a nice pretty 1. So then our other sort of what-if vertices, if we had an ellipse, we would move left and right by root 3. Since our x minus 1 squared was over root 3. So our center, recall, was at 1, negative 4. So 1, I'll move left root 3, and we'll stay at negative 4. Then 1 plus root 3, and again stay at negative 4. So let's put all this into a sketch. So our center, 1, negative 4. Vertices, 1, 1, and 1, negative 7. Foci, negative 4 plus and minus 2 root 3. 2 root 3 is, recall, came from root 12, so it's 3 and change. So negative 4 minus 3 and change is negative 7 and change. So we're not quite to negative 8. So the foci are pretty close in on this guy. Same thing going then up the same amount. So there's our foci. Then our sort of what if ellipses, square root of 3 is smaller than square root of 4, so it's smaller than 2, so it's 1 and change. So 1 minus 1 and change is negative, and between negative 1 and 0, and 1 plus 1 and change is 2 and change. So we can make our little box here. remember this one opens up and down. And we'll do again, just for time, I'll only find one of the asymptotes on the example. I'll have you find the other one. So our hypothetical one to the right, we went to 1 plus root 3 for the x. And we topped out at negative. That's why it's. I graphed 1, 1 instead of 1, negative 1. My apologies. That's why my diagonals were looking wonky. Okay, so I'm going to cut my drawing off there. So this is a little bit further down there. So 1 plus root 3 for the x. As far as our height should be a negative 1 there. And on the bottom end, we have, we went left to 1 minus root 3 for this corner, and we went down to a negative 7. So our slope for the first asymptote, change in y over change in x, negative 1 plus 7 over 1 plus root 3 minus 1 minus root 3. So we have 6 upstairs, and then let's see, the 1's drop, and root 3 plus root 3 to root 3. So this is 3 over root 3, which is 3 root 3 over 3, which is just root 3 for a slope. So then change in y is slope times change in x. So y plus 1 is root 3 times change in x. So y plus 1 is root 3 times x minus 1 minus root 3. So y equals root 3x minus root 3 minus 3 minus 1. So y is root 3x minus root 3 minus 4. So that's one of our two asymptotes. Okay, so some problems I would recommend trying out. This was in section 10.4, 15 to 61 on the odds. And I'll try to create a similar one for the My Math Lab fans out there. If you have questions, please get in touch. Otherwise, I'll see you next time. Please stay safe out there.